Okay, hello everyone. So in my last video, we had seen these three expressions for self-inductance. Okay, so let's continue our analysis, and I'll be giving you an examples how these expressions can be used. Okay, so let's look at this question here. So the question you can see on your screen, that is, the field winding of a DC electromagnet is wound with 960 turns. Okay, so the number of turns in a certain winding is 960 and has a resistance of 50 ohms. So the resistance of the field winding is 50 ohms. When exciting voltage is 230 volts. So if you recollect, the DC electromagnet will be something like, so it will have some resistance also. So the resistance is 50 ohms, and it's supplied by a voltage of 230 volts. And the number of turns is 960. I'm just putting it in a diagram. The magnetic flux linking the coil is 0.05005 Webers. Okay, so the flux is also given. So 0.005 Webers or 5 milliwebers. Calculate the self-inductance of the coil and the energy stored in the magnetic field. So self-inductance of the coil, first I should find what is the current in the coil. So the current is nothing but voltage by R, because I am applying 230 volts and the resistance is 50. So 230 divided by 50. So 23 divided by 5. Let's use a calculator. So 23 divided by 5. So I'm getting 4.6 amperes of current. And we know that from the first formula, that is, inductance is nothing but N phi by I. So everything is there. So now I can find the inductance. Inductance is nothing but N phi divided by I. So 960 turns multiplied by 0.005 Webers of flux divided by 4.6 amperes. So this will give me the inductance. Okay. So let's use the calculator. So 960 multiplied by 0.005 and divided by 4.6. Okay. So I'm getting something like 1.04347. So 1.0437, I'll just round it off to 4 henries. Okay, so this is the inductance of the coil. Now another part of the question is self-inductance of the coil and energy stored in the magnetic field. So how do you know the energy stored in the magnetic field? So we have not discussed this concept, energy stored in the field. So just for the time being, you can just use the formula half Li square. Okay. So half into 1.044 into 4.6 square. So this is the energy stored in the magnetic field. So let's calculate that. So 1 divided by 2 multiplied by 1.044 multiplied by 4.6 square. So I'm getting 11.04 joules of energy. Okay. So this is the energy stored in the magnetic field. So this is the first example. Okay. Let's look at more examples and just going forward. So I have already prepared some more problems. So this is the second problem. An iron ring 30 centimeters mean diameter is made of a square of iron 2 centimeter by 2 centimeter cross section. So the moment you see the length and diameter and all these things, the geometrical properties are given. So let's to understand it, let's quickly draw the diagram. So iron ring. Okay, so it's a ring. So I draw the ring like this. So mean diameter. So mean diameter means from the middle point here to middle point here. So this diameter is 30 centimeters or 0.3 meters. So this is the one. Square section. Square is the 4 centimeter square, that is 2 by 2. It's actually a square shape. So cross section is nothing but 2 by 2 centimeter square. That is the cross section, and is uniformly wound with 400 turns of the wire. So it is important to note that it is uniformly wound. That means the coil is throughout this entire circumference of the ring. 400 turns of a wire, 2 mm square cross section. This is 2 mm square, but the cross section of wire is not relevant here. So just I'll show the entire winding. So let's say the winding starts like this, and then the winding keeps on going across the coil like this. So this is the starting and this is the ending of the coil. So this is my winding. So what is the number of turns? So the number of turns is nothing but 400 turns. Calculate the value of self-inductance of the coil. Assume mu r equal to 800. So the core material mu r is 800. That is also given. So if you look at the bunch of formulas that we have, so I think the second one is what is relevant. N square mu naught mu r a by L. Okay. So let's apply that. So I'll come back to my problem. So the question is calculate the self-inductance. So it is N square mu naught mu r a divided by L. So first, so I'll just make some space. So n, number of turns is 400. So 400 square multiplied by mu naught, 4 pi into 10 power minus 7. That is a constant, this mu naught. Absolute permeability. Again, you had seen this several times. Mu r, relative permeability is 800 given in the question. Area of cross section is 2 centimeter by 2 centimeter. So I'll write it as, so the cross section is 4 centimeter square, or 4 into 10 power minus 4 meter square. So I am converting centimeter square into meter square. So 4 into 10 power minus 4 meter square. So whole divided by the L. Okay. So what is the length of this thing? And the diameter is given. So the length of the entire core, or length of the coil itself. Okay. So the length of the coil will be, if the diameter is 0 0.3 meters, so the circumference will be pi d. Okay, so this will be the circumference. So I'll just write pi into d. So this is my entire formula. So let's simplify it. So I can cancel pi right away. Okay, so 400 square, there will be 2 zeros, and square there will be 4 zeros. So I'll just cut everything. 4 zeros and 10 power minus 4 I can cancel right away. Then what do I have? By the way, this square applies here. So 4 square, it will become 16. So let's now use a calculator and simplify it further. So let's look at the numerator. So I have 4 square here. Okay. So 4 square in the numerator up to here. Then one more 4. So multiplied by 4. Pi got cancelled. Then 10 power minus 7. Okay. So I have 10. Sorry, I'll just start it from beginning. 4 square multiplied by 4 multiplied by 10 to the power of 7 with a minus sign is this one. Then 800, so multiplied by 800. Then I have 4, so 4. This is got cancelled, and then finally this everything is divided by 0.3. Okay. So 0.3. So finally my answer is 0.068266 so on. So I'll round it off as 0.068266. 0.0683. Okay, so 0.0683 Henries, or I can say 68.3 millihenries. Okay, so this is the inductance of the coil. So this is an example where you are able to find the inductance when the geometrical properties are given. Okay. So this is about the second formula how we are using. Okay. So this one. So I have one more question for you. So if I just go down, so this is another question. Let's work on this now. So if a coil of 150 turns is linked with a flux of zero point 0.1 webers, so okay, so directly the data is given. Number of turns is 150, and the flux is 0.01 webers. When carrying current of 10 amperes, okay, calculate the inductance. Again, N phi by I equal to L. So 150 into 0.01 divided by 10. Okay. So 15 into 0.01. So it is 0.15 Henries. Okay. So this is the inductance of the coil. If this current is uniformly reversed in 0.01 seconds. So basically what they are doing is they're reversing the current. Okay. So imagine that there is a coil of 150 turns carrying a current of 10 amperes. Now suddenly the 10, not suddenly, within the time of 01 dt is 0.01 seconds, within the dt the current is reversed. So that means the what is the di? Okay. So di is the plus 10 current becomes minus 10 current. So 20 amperes is the change in the current. So di by dt I can calculate. Calculate the induced electromotive force. Okay. So I know electromotive force is nothing but minus L di by dt. So therefore minus 0.15 into di is 20 and dt is 0.01 seconds. Okay, so how much is this? So I can cancel all this and this point. So 15 into 20 is 300 volts with a minus sign. So 300 volts are induced in the coil. The minus sign signifies that the current will try to maintain will be induced opposite to the original induced EMF. Okay. So this is one more example where you can use this kind of formula, okay, for the inductance. So I hope you are learning some applications of this inductance. So inductance is a very important property of the it's a electrical property of the materials. So using these three problems, I hope you had got some idea about it. So let's see if we have more problems. Yeah, so again, to summarize, kind of remember these formulas. So these are three ways you can define the self-inductance. Thank you.